What if you could make any amount of money with the fewest coins possible, no matter how weird the denominations? CoinChange is a Pattern Mastery 100 legend and a favorite at Apple, Facebook, Microsoft, Salesforce, and Amazon interviews. This dynamic programming classic tests not just your DP chops, but your ability to break a tough problem into smaller, reusable subproblems. Let's crack the pattern that unlocks hundreds of interview questions. Let's break it down. You're given a set of coin denominations and an amount. Return the minimum number of coins needed to make that amount. If you can't make it, return -1. You can use as many coins of each denomination as you want. Now let's assess our approach. Brute force would try all combinations. Exponential time. Instead, this is a perfect fit for dynamic programming. For every amount from 1 to the target, we'll keep track of the minimum coins needed. At each step, we look back at the best answer for current amount, each coin. This bottom-up DP builds the answer efficiently, and we only need a simple array. Here's the plan. Create a DP array of size, filled with amount +1, a value bigger than possible. Set DP0 equals 0, 0 coins to make amount 0. For each amount from 1 to the target. For each coin, if coin less than or equal to current amount. DP amount equals min DP amount coin +1. If DP amount is still amount +1, return -1, else return DP amount. Let's try to implement it using solution 1. We begin by defining a class called solution. This simply organizes our method neatly, like putting the entire approach inside one toolbox. Inside the class, we define a method named CoinChange. It takes two inputs. Coins, a list of coin denominations. Amount, the target we want to reach using the fewest coins. Our goal is to compute the minimum number of coins needed to make that amount. Here we create a DP array of size amount +1. Each position represents the minimum coins needed to reach that exact amount. We fill it with infinity to indicate that we haven't calculated anything yet. Think of it as starting with all values set to impossible. Time complexity for this initialization is O amount. We set the base case. To make amount 0, we need 0 coins. This is the foundation that all other answers build upon. We begin looping through every amount from 1 up to the target amount. For each amount A, we want to determine the minimum number of coins needed. This loops amount times, so O amount. For each amount, we iterate through every coin denomination. We ask, can this coin contribute to building amount A? This inner loop runs len coins times, giving us an overall time complexity of O amount times number of coins. We check if the coin is usable. If a coin is at least 0, it means this coin can help form amount A. Otherwise, it's too large and we skip it. This is the heart of the algorithm. To form amount A, we look at amount A, coin. If we already know the best way to form a coin, then adding one more coin forms amount A. So we update DPA with the minimum between its current value and the new calculated value. This fills in the table using previously solved subproblems, classic dynamic programming. Finally, after completing the DP table, if DP amount is not infinity, we return it, meaning the amount is reachable. Otherwise, we return -1, indicating it's impossible to form the target using the given coins. Test case explanation, CoinChange, dynamic programming case 1, coins equals 1, 2, 5, amount equals 11. Let's test our function using this input, 1, 2, 5, with an amount of 11. These values represent the available coin denominations, and the total amount we want to make using the fewest number of coins. Here's why the solution works. We build a DP array where DPA stores the minimum coins needed to form amount A. Starting from 1 up to 11, we test each coin and update the table. For amount 11, the optimal combination is 5 + 5 + 1, which uses 3 coins, the fewest possible. And that's exactly what our program outputs, 3. The DP transitions work perfectly. So, our implementation is correct. The algorithm successfully determines the minimum number of coins needed for any given amount using bottom-up dynamic programming, efficient, accurate, and reliable across all test cases. Let's try to implement it using solution 2. We begin by defining a class called solution, just our container for the coin change method. Think of it as the toolbox where all the logic will live. Inside the class, we create a function named coinChange. It receives two things. Coins, the list of coin denominations. Amount, the total we want to make. Our goal is to find the fewest number of coins needed to reach that amount. We set up a dictionary called memo. This is our memory box. Whenever we compute the minimum coins for some remaining amount, we'll store that result here. This prevents repeating expensive work and brings our time complexity down to roughly amount times number of coins. Here we define an inner helper function called DFS, short for depth first search. This function tries to compute the fewest coins needed to reach a remaining value rem. We check if the remaining amount is 0. If we've reached 0, we've successfully formed the amount. So in that case, we return 0 coins, because no more coins are needed to finish the amount. This acts as a base case for our recursion. If the remaining amount becomes negative, that means we overshot. We used too many coins. This isn't a valid path. We return infinity here to mark this path as unusable. In our comparisons later, infinity signals, don't pick this route. Before doing any work, we check if we've already computed the best answer for this remaining value. If it's in our memo dictionary, no need to repeat the calculation. If we've solved it earlier, we return that saved result immediately. This is what makes this approach efficient. We start with a variable min_coins, initially set to infinity. As we explore different coin choices, we'll update this to the best, smallest value we find. Now we iterate through every coin denomination. For each coin, we try subtracting it from the remaining amount and see if that leads to a solution. This branching process is where the DFS explores multiple paths. We recursively call DFS with the updated remaining amount. This asks, if I use this coin, how many coins would I need to finish the rest? If the recursive result is an infinity, it means the remainder was solvable. So this is a valid path. We update min_coins by taking the minimum between the current answer and res +1, where +1 represents the coin we just used. This is the key dynamic decision step. After checking all coin choices, we store the best result for this remaining amount in our memo dictionary. This prevents recalculating it later and dramatically speeds up the overall process. We return the best, smallest number of coins we found for this remaining amount. The recursive stack will now work its way back upward. Now we initiate the whole process by calling DFS amount, asking, what's the minimum number of coins needed to reach the full target? Finally, if the result is an infinity, we return it. That means the amount is achievable. Otherwise, if it's still infinity, we return -1, meaning it's impossible to form the given amount with the provided coins. And that's how this algorithm works. It first initializes memoization to avoid repeated subproblems, then uses a depth-first search to explore all coin combinations, caching results as it goes. Efficient, simple, and elegant. Solution 2. Case 2. Now let's test this input, 2, with an amount of 3. This means the only coin we have is of value 2, so we can only form even amounts. Here's why the solution works. DFS checks all possibilities, but subtracting 2 from 3 gives a remainder of 1, and subtracting 2 again goes negative. Because no combination ever reaches exactly 0, the algorithm returns infinity, which we convert to -1. And that's exactly what our program outputs, -1. Perfect. The solution correctly identifies that amount 3 cannot be formed. So, overall, our implementation is correct. The algorithm successfully computes the minimum number of coins, handling valid cases, impossible cases, and base cases with reliability and efficiency. Let's wrap up with a quick recap of the coin change problem, one of the most classic examples of dynamic programming in action. Breakdown recap. We began by understanding the task. Given different coin denominations and a target amount, we needed to find the fewest coins required to reach that amount, or decide it's impossible if no combination works. Assess recap. We compared potential strategies and realized that brute force recursion would try every combination, quickly becoming inefficient. Instead, we chose a bottom-up dynamic programming approach, where we build up solutions for smaller amounts and use them to solve larger ones efficiently. Structure recap. We structured our logic around a DP array, where each index represents the minimum number of coins needed for that specific amount. By iterating through all coin values and all subamounts, we continuously updated the array with the smallest count possible. Implement recap. After setting up the DP logic in LeetCode, our implementation ran smoothly, efficient, clean, and easy to follow. Check recap. We tested it using multiple inputs on LeetCode. confirming that the solution handled all cases correctly, including the ones where no valid combination exists. The key takeaway here is that dynamic programming shines when problems can be broken into overlapping subproblems. By building up from smaller results, we turn a seemingly complex challenge into a simple, systematic solution.